The topic I'm going to discuss is Bertrand Russell and geometry. Basically, I would rather like to uh, place this lecture in a broader theme, how geometry as such, the evolution of geometry, historically, conceptually, logically, mathematically, how we place it in the larger episteme of mathematics and in physics also. And with particular anchor, I would rather like to place the discussion with a particular uh, essay of Bertrand Russell, which is has partly written as a part of his dissertation on the foundations of the geometry. So earlier part of the 19th century, so there have been various debates how mathematicians and philosophers did view mathematics, and how with the different branches of mathematics, algebra, geometry, analysis, arithmetic, how they somehow interfaced with each other, and how also they interfaced with the larger developments in the sciences also. Not only sciences, with the larger the spirit of age, or a larger philosophy which was prevalent at that time. So one important thing in the uh, earlier part of the or later part of the 19th century or the beginning of the 20th century was how the the geometry, how we try to visualize geometry in the Euclidean sense, the maybe 2500 years, how the Euclidean elements and the Euclidean formulation not only of mathematics, but also mathematics in geometry, but also Euclidean influence of how we even try to visualize Newtonian mechanics also. So the frame of mechanics was Euclidean in a sense. So, but the pinnacle or the way somehow Immanuel Kant as a philosopher tried reformulated the notions of Euclidean space in his uh, in his critique of how he categorized transcendental aesthetics, and where he categorized the notions of a priori and a priori geometry, and how he somehow placated or located space and time as a priori in certain constructions, and the relationship of Euclidean geometry to somehow uh, the a prioriness of Euclidean geometry. So that was an important element, how Immanuel Kant somehow placed geometry. So I would rather say the way Russell has written, or the very various people. This is the one part of it. The other part of it is that the developments in Euclidean and non-Euclidean geometry, how the notions of the fifth postulate, that to each point in an to each point there can be uniquely one line can be drawn parallel to that point. So which was somehow in the literature, there is how the interesting part of it, how people like Bolai, Gauss, not Riemann, Lobuchevsky, even medieval times, Nasir Tusi. So they have constructed geometries, the Playfair axiom, hypotheses, or various, how we can also construct the alternative constructive systems, having modifying the fifth postulate of Euclid, and we could develop equally consistent systems. So the development in a sense was considered maybe revolutionary or rather path breaking, or even you can see it bordered on sort of apostic. There was a sort of apostic element even to divulge it in the research community because of the what I should say credibility, or the heavy credibility of the credibility of Euclidean geometry since centuries was considered as immutable in the larger constructions of things, whether mechanics, physics, or larger discourses in mathematics. The way Euclidean elements have a sort of canonical or a respect to it. Be that is may is it be that what it may be, the history of non-Euclidean geometry is as much interesting. But the point what I want to emphasize is that the way Bertrand Russell has located his essay Foundations of Geometry is basically in large part he has tried to see that the Euclideanization of the space by Kant somehow, and the a prioriness of that very thing was somehow for some mathematicians it was an impediment to move forward, and maybe but for some mathematicians they outrightly wanted to reject it. For some, they wanted to modify certain assumptions of that a prioriness of the space which we constructed. So, so the Russell, the influence of Kant, maybe a lot of people might negate him that his influence had been negative, or rather, he it could be positive in the sense that in the background discourse where he had localized space and time as a priori elements, and the idea of geometry, the idea of geometry, and the idea of space. So, so the a priori identification of space with the geometry somehow placed geometry in a sense independent of the empirical sciences, the way we define empirical sciences. So which was somehow in a sense the way the different branches of mathematics, whether arithmetic, whether analysis was developing. So the placement of geometry as independent of what I should say, as independent of what I should say, empiricality of the things or a prioriness of the things was an element of Kant, which somehow the lot of energies of mathematicians and philosophers had gone to negate it, critique it, or bypass it, so that the main debate of going from transition from Euclidean geometry to non-Euclidean geometry could be made what I should say plausible for the next generation of thinkers or researchers. So maybe his Kantian, so even people like Russell, people like Helmholtz, people like Riemann somehow did not maybe Russell has given a very good biography how people like Erdmann, Helmholtz, Riemann, even Lotz, even though Lotz was a follower of Kant, but somehow he did not reject Kant in his understanding of geometry. And the case of Klein being that he had a different view. So this is this part of it. So the a priori, so the way we talk of analytical truths and synthetic statements. So in analytical statements, the subject and the predicate was somehow, for example, in the Leibnian dictum, the subject and predicate, the definitions could somehow cohere. While in case of Kantian thing, that so maybe the how we define, basically I'm coming to the thing, that the way of trying to logicize geometry, so how much it was plausible. So the Kantian way of understanding that the geometrical axioms or geometrical statements were a priori not analytical statements, a priori synthetic statements, but the a prioriness was somehow extended to the Euclidean geometry only, because the non-Euclidean geometry were discovered. We can't, we could in principle extend the a prioriness of the Euclidean geometry to the larger non-Euclidean geometry also, which they may be which may be self-consistent and possible, which Russell did in a way in his thesis, um, extending the argument not only from Euclidean geometry to the non-Euclidean geometry, but the a prioriness of the synthetic statements somehow did militate that space exists a priori. It's not being constructed. We don't construct it. So the debate can, if we want to, I would rather try to digress it. The debate can be largely, what I should say, and you can digress the debate into what is mathematical truth and what is the physical truth. So if geometrical statements are a priori statements and they can exist independent of the empiricity of the world, so what is the truth content of the geometrical statements? Or you can digress the question to what are mathematical truths and what are the scientific truths or empirical truths. So do scientific truths or empirical truths, do they somehow, what I should say, differ, or what I should say, they mathematical truths or the scientific truths, mathematical truths are the abstract elements which scientific truths are bound to follow. Pertinent to it may be the famous debate, famous essay of the Eugene Wigner of unreasonable effectiveness of mathematics in natural sciences. So he is talking of large debate of mathematics, but here I'm trying to placate, I'm trying to place the geometry or geometry, whether first geometry can be traced to how, where would you place geometry in the larger subject of mathematics, and if geometry is, and what are geometrical truths, what is the epistemic content of the geometrical truths. So this is this much. So for example, so this is this much I am how so now I'm right there. There are some statements, for example, I will rather. So before I'm going to touch the larger scope of geometry, whether it's an empirical science or it's a part of a branch of mathematics or it exists a priori ness. So are geometries which we construct mere pure constructions of human mind, and we can make as much as self-consistent constructions as we can have, and we can have as much geometries as we can have. The case being particular that of the non-Euclidean geometry. So you can have as much many self-consistent geometries as much possible. The self-consistent geometries may not be consistent with each other, but they might be internally consistent within their own system. So does this thing have to say this thing have this these constructions have to say uh, a larger thing to the questions of the relationship of geometry to mathematics and mathematics to the empirical feature of the world which we are constructing as a part of physics or a part of a science. So one thing you can connect is that in mathematics there are three things. Maybe there is consistency, there's independence, and there is completeness. These are three conditions. But in case of if you just say in Euclidean and non-Euclidean geometry, so there is something called independence. So independence of the things. So you can construct the fifth postulate or the alternate system of geometries independently, starting from the same assumptions. For example, if A goes to B, you are not concerned whether C, D, E also goes to B. So you start from A and you arrive at B. But in the similar events, E, F, G, H can also go and come at B. So you are at a given point in time interested in A goes to B, but you will separately construct think whether C also goes to B or D also goes to B. So whether how A and D are, the other systems are related, can we start from because the normal understanding of axiomatic structure is we are going to reduce all the statements theorems to some primitive structures via logic or via formal structures. But the different parts, if we start from different starting points and arrive at the same point, so what the different starting points have a relation to it, so the debate becomes a bit complicated. So you can place it in terms of the notions of independence, notions of self-consistency, and notion of completeness. So you can say what I was saying there. So in a priori, to construct a priori means to find applications in a posterior science. It's an epistemic problem, or if you prefer, a problem about different methodologies of mathematics and empirical sciences. So, so I just quote, for example, there is a statement, for example, it has been the orthodoxy in mathematics to see geometrical intuitions as unreliable. Instead, we should trust only purely algebraic methods. The latter are epitome of rigor, for example. So the algebraic topology notation is somewhat halfway notation between pure algebra and pure geometry. So which, this is also a debate why whether we should take algebraic constructions serious or whether we are going to take mm, geometric construction serious. Because if we locate it in the debate, uh, so algebraic methods were considered more rigorous as compared to the geometrical methods. So in the post facto, if I would rather also want to see it, whether whether the debate of geometry, which was existing at the time, so how the different schools of mathematics, whether formalistic school, axiomatic school, what I should say, intuitive school, how we can look this geometric this the epistemic content of these geometrical these a prioriness or the posteriorness of geometrical truths within the larger domain of mathematics as well as sciences also. So even so the epistemic so it might have different ways of, there may be different ways of looking the same thing by these very different schools, whether it's logicism or whether it's formalism or logicism or inclusivism, where, for example, people like Hilbert, Grover, they might be having, for example, same, they might be having different opinions to the same. For example, for example, Hilbert and Brouwer acknowledge the influence of Kant's philosophy of mathematics and reject Leibnizian tradition, according to which all mathematical propositions are analytic, in the sense that their truth can be demonstrated merely by an application to the principles of logic. So both Brouwer and Hilbert regard mathematical theories as synthetic in the sense of the term, which is based on mutually exclusive and jointly exhaustive classification of propositions into analytic and synthetic. So yet Brouwer's concept of synthetic character of mathematics is very different from Hilbert's and nearer to Kant's, what I should say, near to Kant. So I'm just trying to come to the point which I would rather say is that so how I'd rather come to what Bertrand Russell tries to start in the start of this essay, what he says. For example, Bertrand Russell says that. Bertrand Russell says, for example, where he starts in the foundation, he says geometry throughout the 17th, 18th century meant in war against empiricism, an impregnable fortress of the idealists. So those who held as was held in the continent that certain knowledge independent of experience was possible about the real world had only to point to geometry. None but madmen said would throw doubt on its validity. None but for fool would deny its objective reference. It was only through the creator of modern epistemology, that geometrical problem received a modern form. He reduced the problem to, for example, if geometry had an apodictic certainty, means sure certainty, as such must uh, be purely subjective, and conversely, if space is purely subjective, geometry must have a apodictic certainty. Means apodictic means it ought to exist. There is a specific meaning to it. So a certain meaning to the thing. And the further, what is the connection between subjective and a priori? Would experience be impossible if certain axiom is or a postulate were denied? This is one question. Or would experience as to subject matter of science be impossible without a certain axiom or postulate? So what pieces of knowledge are a priori, but rather depends upon on that determination and belongs in any case rather to metaphysics than. So apodictic means self-evidently true. So the liquidification of maybe Euclidean orthodoxy by the dismantling of that by the construction of axiom of parallels, as was suggested by Gauss and many other people. So it somehow laid to rest, for example, certain the contradictions. So a prioriness of the Euclidean geometry was somehow, in a sense, critiqued. But you can also say there was an a prioriness. You can extend the a prioriness of not only Euclidean geometries but also to the a prioriness of the non-Euclidean geometries. So here I would rather like to say is that, for example, uh, so there's a notion of term called curvature, which was invented by Gauss. So there he how Russell goes through this essay on foundation of geometry. He has classified various eras and times, the first period, the second period, the third period, where he has somehow classified the various developments in the geometries and has tried to locate the larger debates of geometry within these, whether it was Euclidean geometry or whether it was non-Euclidean geometry. In the larger paradigm of maybe even philosophy, also epistemology, also, as well as various renderings of mathematicians, renderings of not only mathematicians but also philosophers also. So particular case being there that of von Helmholtz. So maybe von Helmholtz was one person who was not only physicist, he was also physiologist also. So he was a bit post Riemann, but his arguments were more. They did not characterize the rigor. You cannot as rigorous as that of Klein or Riemann, but they had a philosophical element to it. So what? For example, not only Gauss, Riemann, Hilbert, Herbert. So what I would rather say is it that I would rather uh, placate. I would rather make one statement that in the history of non-Euclidean geometry, there has been always, or in the process of getting away from the Kantian paradigm, so there have been people, and there has been a strand. So maybe Gauss influenced Riemann. Riemann was also influenced by Herbert. If you read Russell's thesis, in the same way how Helmholtz. So there's a good, interesting interplay. So you can just trace it, that even the Einsteinian way of applying the Riemannian way, how Einstein arrived at it, it was a particular, it was part of that. You can trace it, how he has arrived at it. So there was a person prior to a contributor, there was also a contributor prior to the contributor. So there is a story behind the story, and which is nuanced. But reading Russell's Foundation of Geometry, you can somehow maybe partly you can feel it. So, for example, when he says for beginning with the criteria of one of the points of Euclid's system, preserved his synthetic method, while it threw over one of his action, the later on the contrary being guided by the philosophical rather than mathematical spirit. So this is what he says about Helmholtz. And endeavored to classify the concept of space as a species of more general conception. It treated space algebraically, and properties it gave to space were expressed in terms not of intuition but of algebra. The aim of Riemann and Helmholtz was to show by the exhibition of logically possible alternatives the empirical nature of received axioms. So this was the departure from Kant. Which I will rather emphasize. So Riemann, and the aim of Riemann and Helmholtz was to show by the exhibition of logically possible alternatives the empirical nature of received axioms. So geometry independent of empiricity, so it was somehow critiqued. So this was the first part of it, the first period. In the second period, what Russell says in the second period, the aim of Riemann and Helmholtz was to show that logically possible alternatives, the empirical nature of received axioms, while their philosophical purpose was to all the axioms of geometry are empirical, and that a different context of experience might have changed them all. The unintended result of their mathematical work was, if I am not mistaken, to afford material for priori proof of certain axioms. So he is giving, so afford material for the so there was a proof, empirical proof that the certain axioms can be taken as a priori. So you can trace the geometrical truths not to the so a priori truths, maybe of what I should say, how we construct space in the Kantian sense, but how even the veracity of the geometrical theorems can be rooted in the empirical constructions. So this is a soft, I will not say soft departure, or how whatever you might want to say it. So there is a divergence between Riemann and Helmholtz, the philosophers, and so now I'll rather come to the concept of a manifold. So the general purpose of so he is articulating the way Riemann tried to define things. So the general purpose of concept so now going from Russell's dissertation, in his dissertation he is talking of the dissertation of Riemann. Maybe that was also read by had a significant influence on Einstein also in formulating his general theory of relativity. So what he's saying, how he defines conception of manifold. The general purpose of Riemannian dissertation is to exhibit the axioms as successive steps in the classification of species, means space. To the absence of this conception, Riemann attributes the obscurity with which on the subject of axiom lasted from Euclid to Legendre. So Riemann succeeded from an algebraic point of view in exhibiting far more clearly than any of his predecessors that axioms which distinguish special geometry from the quantities with which mathematics is conversant. This brings us to remaining other fundamental conceptions, which is even more fruitful than that for manifold. So after this, maybe I'll just wait a second. So so the concept of not only Riemann, so how in the Gauss is how he defined curvature. So measurement of curvature. How Gauss try to define the measurement of curvature from point to point and from space to space. So how maybe I'll rather see how this geometrical statements of, for example, not only Gauss, Riemann, and Helmholtz, but maybe there's a statement of maybe Poincaré also. For example, when he says, "What ought one to think? Is Euclidean geometry true?" So now the question is now it entails us to ask. So if there are going from Euclidean geometry whose a prioriness was considered very much as a truth statement, so entailed a question that is Euclidean geometry true? So for Poincare, he says that the question is nonsense. Geometrical axioms, according to him, are mere conventions. They are definitions in disguise. Or, for example, if we study the non-Euclidean geometry, the very notions of congruence, how we define congruence in Euclidean geometry and congruence in non-Euclidean geometry, and the relationship of distance between 2 points is modulo the logarithmic ratio of anarchic ratio of the same 2 points between the non-Euclidean geometries. And we can construct the truths, what is the correspondence of the truths of Euclidean geometries to the uh, statements or conclusions of assumptions of Euclidean geometry or conclusions of Euclidean geometry to that of non-Euclidean geometry, or things which are true in Euclidean geometry, are they more, are they true in non-Euclidean geometry also? So which I'll come to the maybe the very interesting topic of how the if the Euclidean geometry was the perfect frame, or it was the ideal way in which Newtonian mechanics could be formulated with the prior conception of space and in which particles are moving, universes. So, so how was non-Euclidean geometry more useful in comparison to the Euclidean geometry? Or does it say something more about the veracity of non-Euclidean geometry as compared to Euclidean geometry? Or they are just mere constructions to explain the world, to map to explanations to map the empirical aspects of the world? But the empirical aspects of the world may our understanding our may vary from time to time, depends upon our range of uh, our it also deals with the observational aspects of the universe or matter. So it may be also, it may vary our from time to time. So the a priori constructions of Euclidean, non-Euclidean, or any other general statements of general geometry, do they have to uniquely say something about the physical world, or they are free imaginations of mind and our way of relating those, not imagination, free imaginations, or maybe logical consistent constructions of mind, or not only logical, mathematical or geometrical constructions of mind which may map to certain physical problems. So is that thing unique or not? So it is a very, it might be an interesting question. So the question I would is maybe this time I'm going to address it in terms of the debate of Euclidean geometry, non-Euclidean geometry, Kantian understanding of space-time with regard to the a priori and the posteriori nature of that space-time within the larger understanding of Russellian thesis of foundation of geometry, and the larger debate how we construct the mathematical truths as well as geometrical truths. So, for example, what I'm going to say is that, for example, which I was talking, how we construct a distance in Euclidean geometry and how we construct distance in non-Euclidean geometry. For example, Cayley had showed that in Euclidean geometry, distance may be expressed as the limit of the logarithm of the anarchomorphic ratio of 2 points and coincident points at on the one on the straight line. It follows that the projected definition of distances we shall obtain precisely the formulas of hyperbolic, parabolic, or spherical geometry. Accordingly, as we choose the point to which the value infinity is assigned at a finite, infinite, or imaginary distance from the point of which we assign the value 0. So, metrical definition of distance is same in Euclidean and in non-Euclidean space. Therefore, to argue in its favor uh, therefore to argue in is to in favor of Euclid. So there is a famous, good, important statement of Cayley who says, so in Euclidean geometry, the distance may be expressed as the limit of the logarithm of n harmonic ratio of 2 points and coincident points at infinity on their straight line. While if we assume that the points at infinity were distinct, we obtained the formula for distance in the hyperbolic or spherical geometry, according as these points were real or imaginary. So no ordinary meaning of distance is required in non-Euclidean as in Euclidean geometry. Indeed, it is only in the metrical properties that geometries differ. So this is what I have said also. It's restating the same thing. So how we can make a possible relation of Euclidean geometry and non-Euclidean geometry, and how we can define the definition of congruence basically, so which will come later. So how can we make parallels between Euclidean geometry and non-Euclidean geometry? So there one important thing which maybe Russell has this very good paragraph in which he says, for example, when he says that as the mathematical results shook themselves free from philosophical controversies, they assumed gradually a stable form from which further development we may reasonably hope will take a form of a growth rather than transformation. When philosophical motives cease to operate, this is in general a sign that the future belongs entirely to mathematical technique. So when this stable stage has been attained, it is time for philosophy to borrow of science, accepting its final premises as those implied by the real necessity of fact or logic. So maybe he has saying that the churning which was the philosophical churning, the churning which was taken within the context of trying to negate Kant or trying to accept the non-Euclidean geometry as possible alternative systems, as we have taken Euclidean geometry for many centuries. The churning, it somehow culminated to a stage where people started formulating these debates in some exact mathematical statements or formulas, and we have reached a technique. We have for example, we have the in general a sign that the future belongs entirely to a mathematical technique. So the faith in the mathematical the faith in the technique, which whether it was Beltrami, clean, so the formulas which we dished, which came out of it. So people, rather than again going to discuss those debates, maybe it culminated or into something very concrete in terms of some mathematical formula. So the comment of Russell is that the aim of philosophy, what I should say would be, is to the philosophers should start as their starting point should be the final point, the final points which has culminated in terms of techniques. Philosophers should take them as given as the starting points and then philosophize. So maybe there's a comment by Gauss who says that he commented on Hegel that his comments on maybe mathematics is muddle-headed nonsense. So maybe Russell might be partly responding to that also. This is my hunch. I don't know. Maybe I'm wrong or right. So now I'm coming to what is how we define a metageometry. Metageometry means you try to define foundation of geometry. So the debate which culminated here ultimately. So you can say how we define geometry. For example, conditions for the existence of space constants, constant measure of curvature, which is equivalent to homogeneity of space. So how we try to within this debate, how we try to visualize geometry. So this is one axiom. The second axiom is space has finite integral number of dimensions. That is in metrical terms that the position of a point relative to any point in space is uniquely determined by finite number of dimensions. So you can have finite. So in Euclidean space, 3 was important. In Einstein space, maybe time 4. So in Euclidean space, 3 was important. So how we went from 3 to n, or how we can start from 3 dimension and go for n dimensions, or how we can go from n dimensions to come to 3 or 4 or 5, or how we can go from higher dimension manifold and take the submanifold in that manifold. So it came later after this thing. First, how the formulation of Euclidean and non-Euclidean geometries in crisp sense, and dishing them out of those philosophical that swampland, whether geometry is empirical or whether it's a priori, whether non-Euclidean geometry is possible. So these are crystallized axioms. So first axiom is that how we measure curvature. The second is whether a point in space can, what are the number of dimensions, and the third axiom is to distinguish it from corresponding projective axiom, the axiom of distance. There exists one relation, say, between any 2 points, which can be preserved unaltered in the combined motion of both points, and the relation is called distance. So this is the way we define it. So these three definitions are essential axioms taken from Helmholtz and amended by Lee. This is what so metrical geometry, though historically prior, is logically subsequent to projective geometry. How we map the normal geometrical points to in some projective space. So that's called projective geometry. So in the same way, how we have axioms of normal metrical geometry and how we have axioms of I'm going to state them because they will because basically my interest is basically to emphasize on the role of Euclidean, non-Euclidean geometry, maybe in the empirical part of the things, how the developments in general theory of relativity later. Somehow I wanted to see things in that very larger debate. So I would rather set the stage later and see how the work of Riemann and how these philosophers, mathematicians, how it they interface with each other, and a larger question of the geometrical truth and the mathematical truth and the physical truth. So how, in the context of the geometries, Riemannian geometry or non-Euclidean geometry and general theory of relativity, I would rather, my interest would be, I would rather try to focus. But before I'll just focus on that very thing, I would rather want to set the stage. So first we have talked of the axioms of metrical geometry, and then there are also axioms of projective geometry. So there are so in the debate, if you read some sections of Principles of Mathematics of Russell, he talks of metageometry, projective geometry, and maybe this metrical geometry and the relations between them, and how we can formulate the notions of distance, point, line, plane. So how we can, there are ways, the same different ways of defining the same things. So how we define a line or a plane in one system, how we define the same thing in the another system, and how we can map one geometry with regard to the other geometry, and how we can formulate those systems with regard to each other, the way we have relations of Euclidean geometry and non-Euclidean geometry, and we can have correspondences between the two. So in the axioms of projective geometry are that space is continuous and infinitely divisible. For example, the zero of extension resulting from infinite division is called a point. So any 2 points determine unique figure. 3 points are not in one straight line determine a figure of 3 dimensions. So these are as simple as that. So these you can say. So these are equivalent to the axioms of metrical geometry, explained without reference to quantity. So, so I'll just quote him. So what Russell, we have traced the mathematical development of theory of geometrical axioms from first revolt against Euclid to the present day. Importance of geometry hardly exaggerated. So if we have chronology to it, when Descartes gave us the method of analytical geometry, so there is a Spinoza's influence of geometries. So Newton's belief in the absolute space was held supreme, but Leibniz had different opinion. So against Hume's empiricism was directed the keystone of the critical philosophy, the Kantian doctrine of space. Maybe Hume had a different, he had an empirical way of looking at space, and it was a bit militant, or it was against the way Kant tried to influence, define space. So maybe, but if you say Kant, in some sense, the later, the intuitionists, whether it was Brouwer or Hilbert, so they were more closer to Kant as compared to maybe Leibniz. So it's a side comment, but what I would say is right that geometry has been thorough of supreme importance in the theory of knowledge, Kant. So geometry has been through of thorough and supreme importance in the theory of knowledge. So in the larger construction of how we construe knowledge, so how he defined space or how he prescribed space, so it had a different element into it. So in process of dismantling certain Kantian notions, so even if we are not interested in Kant as a historical, his understanding of space, books, textbooks don't talk of that. It might be a historical like curiosity, or people like Helmos, I mean Russell has somewhere written, or maybe other book. He that the way if you read papers of Helmos, Riemann, Klein, they have written about their developments in geometry as if they don't know about the Kant, the notions of Kant, because so much it might have been dominating or negating. My point to emphasize is that in dismantling thing which is great. Even I would rather say that uh, trying to negate something and getting something very substantial. What you are negating it, investing that and then energies in negating that, it might have some logical value or philosophical value, whatever that may be, or historical value. So I would not want to. So Kant's view on subject true or false have so dominated subsequent thought that whether they were accepted or rejected, they seemed equally potent in forming the opinions and manner of exposition of almost all the later writers. So this is what I was trying to just restate rather. So here I'll just rather restate some statements. For example, the question is how is geometry apoiotic? Means self-evident statements. On the one hand, geometry is known to have apoiotic certainty. Therefore, space must be a priori and subjective. On the other hand, it follows from the grounds independent of geometry that space is just subjective and a priori. Therefore, geometry must have an apoiotic certainty. Space is an intuition, not a concept. So maybe these are statements. So, so before I'm going to just come to my distinction. For example, I'm going to restate some of the sentences of. I'll just restate them. For example, Kant's logical position. Before I'm going to set the stage for how the Kantian understanding of space and Riemannian understanding of space, and then to space, to the how Einstein appropriated Riemannian understanding of space in physics, and how it led to larger question of the relationship of geometry to mathematics and geometry to physics and geometry to science. So the larger debate of mathematical truths and the scientific truths, or geometrical truths and the empirical truths. So I would, before coming to that very point, so I would rather maybe not again and again. It might seem boring to people who might be seeing it, but I would rather restate some of the doctrines of how I would rather clarify what say Kant's logical position. For example, the doctrine of synthetic and analytical judgments. At any rate, if this is taken to be cornerstone of the epistemology, has been so completely rejected by most logicians. But Kant's doctrine, if true, it is designed to restrain the critical skepticism, even where it might be effective. The detail of Kantian reason be sound, his results may be obtained by principles of contradiction plus possibility of experience, as well as his distinction of synthetic and analytical statement. So a distinction roughly corresponding to Kantian a priori and posteriori, though less rigid and more liable to change with a degree of organizational knowledge. Kant usually endeavored to prove that synthetic a priori propositions were necessary prerequisites of experience. So, from the standpoint of general logic, laws of thought, and the categories with the indispensable conditions of their applicability will be alone priori. But from the standpoint of any special science, we may call a priori what renders possible the experience, which forms the subject matter of our science. In geometry, to particularize, we may call a priori whatever renders possible experience of extremality as such. So, space is an intuition, not a concept. They could call for much discussion in a special criticism of Kant. In the philosophers that followed Kant, metaphysics for the most part so predominated over epistemology that little was added to that of geometry. So these are some of the statements. So post Kantian things, how somehow things developed. But one thing is that the notions of a priori and a priori, his classification of priori and a posteriori, the notions of space and geometry, though the whether geometry and space do the definitions somehow overlap in the Kantian paradigm, or rather I would say the larger debate where Kant and Hume somehow differed, or where Russell basically wanted to see how he wanted to place Hume, Kant in the debate of how he tried to visualize space. So in trying to negate the position of Russell was, he being in his earlier stages when he was writing his thesis, he was an empiricist, and he had a particular he was influenced by a particular school of mathematics. He had a particular, the way he wanted to logicize mathematics, he in the earlier stages, the Fregen method of arithmeticizing earth, the way logicizing arithmetic. So his influence of that very thing and his particular interest in empiricism might have a significant way. He might have been these two factors would have been very much significant in how he also tried to visualize the Kantian theory of space as well as time in the sense. So maybe, but Kant had, and also his influence, maybe Russell's influence of how of Leibniz, how he tried to see things down from Aristotle to Leibniz. How, if we say that logic is the law, the way we define logic is they are the rules of reasoning. How Leibniz tried to logicize things. Maybe the position of Kant was somehow, in a sense, he could maybe absorb both, some tradition, some part of this, not entire part of it, of empiricism, but so he was somehow middle between empiricism and this idealism. So what Russell maybe was influenced on the one hand by the project of this Fregen project of arithmeticizing logic on the other hand, and the human understanding of empiricism. So how Hume constructed knowledge is that knowledge can be only constructed from experience. So experiences can be defined from sense perceptions. So that's it. So this was a human way of looking at things. So in the how it the point is that what Russell wants to emphasize, that how he tried to construct the notion of space devoid of construct space with the developments in the geometry, non-Euclidean geometry, and maybe restating or summarizing or adding his own insights to the in the light of non-Euclidean geometry. And in the next lecture I will set the stage. So how he so post Kant. So I'll start with the Riemannian, how Riemannian formulation of space on non-Euclidean geometry was, how Russell tries to characterize it, how Russell sees it, not only Riemann, Helmholtz, Erdmann, and many other people, and maybe how that very thing in the later stages also had influences in the different domains of physics, mathematics, differential geometry, general theory of relativity, and other things also.